And I'd like to thank you all for joining us here today to talk with our friends of Berks Astronomy, Berks County Amateur Astronomical Society. Um, we, of course, are meeting every second Thursday for our, I don't want to call them lectures, but like fun talks with smart people. And then fourth Thursdays is sort of like a hangout, get to know your astronomy club type thing, go over your telescope, talk about space news, this, that, and the other. Um, we just had a Star Watch, which was fun, so stay tuned for more info. berksastronomy.org. Uh, but I'd like to introduce our guests today from Mini Cubes, and they will be talking about a whole bunch of cool stuff. So without further ado, here's Joe and is it Dana
Yeah.
from Mini Cubes.
All right. Thank you, Elon. This is our intern. This is Danya Rose. He
Danya.
is working with us to develop some hardware and software that's relatively new. But I want to explain who I am, what I did to get started, and what we're doing. Now, some of you may remember it was almost 2 years ago. I was actually at the Astronomical Society, and I gave a presentation on PocketQubes then. This is kind of a follow-up to that, but we're going to assume you've never seen anything that we've been talking about, and we're going to start from square one. Okay, I'm going to attempt a screen share. Let's see if this works. Okay, I expect it to explode. All right, and hit the play button. All right, hopefully that worked okay, and you can see the screen. Okay, so MiniCubes LLC is a company that is designed specifically to make PocketQube satellites. So let's start at the beginning. What's a PocketQube? A PocketQube is a microsatellite. These are about 5 centimeters on a side. So think CubeSat, only smaller. Okay. Donnie, would you hand me the three? I know this will be in a very small screen, but this will give you an idea. So this is a 3U CubeSat. Okay. Each one of these sections is considered a U. Right. It was invented by Professor Bob Twiggs back in the late 90s. And he also came up with the idea of a pocket cube, with a pocket cube being this size. So again, we have it broken down into 3 sections, 1P, 2P, 3P. They're essentially 1/8 the volume of a CubeSat. Okay. So why are these important? Okay, well, they're simple and they're possible now because technology has caught up with the concept. The idea of PocketQubes has been around since 2013. It's when the first paper came out explaining what a PocketQube could be, but there was no way to fit everything into the PocketQube size. It just was impossible. What you could probably do was rework an Arduino maybe and get it to fit, but there really wasn't going to be anything of any considerable power in there. Then this revolution really took off. I know this came out in 2007, but really the types of things we could do with a smartphone exploded about the same time. That's when you started to see your image sensors get larger. I mean, right now, I think there's one camera by Samsung that has a 54 megapixel camera on it. That's where we're at. We've created this miniaturization that makes it possible for us to actually fit everything into a PocketQube and make it usable. Okay. Number one, however, is if for astronomers, satellites this big will not screw up your observations. Okay. I don't know how many of you have seen the Starlink trains. I have. I actually have a 10-inch telescope. I've had one come in front of what I was looking at. It does happen. The idea behind a PocketQube is let's take everything that's in these big satellites, let's reduce it to something very small, very compact, and it won't mess with the environment so much. Okay. Okay. So MiniCubes, I have to admit, this has been a lot of fun creating this company. We've developed the PocketQube. We've actually taken it further than anybody in the United States. There are only 3 companies currently on planet Earth working with PocketQubes. There are several research universities working with them, but there are only 3 companies. Okay, there's Minikubes here in the United States. There's Alba Orbital in Scotland and FOSA Space Systems in Spain. That's it. It's a very small market. It started off as a hobby, didn't look like it was going to be possible. And I was working on a 1P PocketQube, which is that big. That's it. That's the whole thing. When we went from hobby and we started to see the potential for commercialization, we decided to incorporate. Minikubes becomes a company. We had a full-fledged LLC in 2018, and the technology is now advanced enough to take it commercial. And when I mean commercial, I mean commercial. We'll talk about the different markets that we're actually working in right now. Minikubes does have customers. We use the term client. We do have several clients. We are preparing to launch a satellite for a client in June. That will go on a SpaceX rocket. That's in partnership with FOSA Systems. They're providing the launch capabilities for us, which is basically FOSA bought space on Momentus. Momentus bought space on the SpaceX Falcon 9. So that's how we get our ride. It's called ride sharing. Okay. This is our entire team. Danya's not pictured because we haven't gotten him into the photo studio to get his picture taken, but we will fix that very soon. You have myself, I have my lead engineer, Nathaniel, and then you have to have all the people who don't do the technical stuff who help you out. That's where Chelsea, Phil, and Tracy come in. Tracy keeps the books so that everything makes sense from a dollar perspective. You have to have somebody be able to work in marketing, and you have to have somebody actually run the operations. That's what Chelsea does. In addition to that, we have advisors from outside the company. These are the people who we consider our core. This is what makes it work. But we also have a network of builders, manufacturers, component makers, researchers who make it possible for us to actually make a satellite. Anybody who says that rocket science is a one-man band is lying, okay? I hate to put it that bluntly, but you don't get to do this as one person. I know this from experience. I've tried. It doesn't work. Okay, so don't even think about it working that way. All right. And also forgive me, Zoom is a relatively new tool to me. I like giving presentations in person. So yeah, we'll go with it. Okay, so what's the technology? And the technology that we're using to build PocketQubes, again, we have these different form factors. I forgot to mention that our total mass on this is 750 grams, or just under 2 pounds. That's all we get for the satellite. This one's actually an Earth observation satellite. It has a very nice lensing system, and we can get some pretty good resolution with it. Our systems are built using additive manufacturing or 3D printing. So we actually make our prototype parts here in our studio, and then they're sent out to be professionally manufactured to closer tolerances at a place called CRP in Virginia. They do a fantastic job with a material called WinForm XT. This is a material that is made to work in space. We're one of 2 satellite companies that are actually using it. It's pretty neat stuff. Okay. By using additive manufacturing, we can rapid prototype. We can be done with a design in weeks and have it ready for testing and ready to go on board a launch craft within months. Normally, it takes months to develop and test and years to get flown. So we've actually shortened that time period, which means these are cheap. Okay, a normal satellite, even a CubeSat, like this particular CubeSat was designed, well, its sister ship is flying on board the Firefly Alpha next month. That is probably $1 million in development and flight costs. Okay. For something like our Earth observation satellite like this one, we can get the price down to about $250,000. Okay, so that's a significant amount of savings. That's why we're doing what we're doing. Well, partially. We can build stuff cheap and effective, courtesy of the way microprocessors have developed. Okay. These types of satellites, depending upon what orbit you put them in, will last up to 3 years. So again, they're literally throwaway, and nothing from this satellite survives re-entry. We don't have to worry about hitting anybody on the head with it. We don't have to worry about it causing contamination on the ground. It is completely and utterly obliterated on impact with the atmosphere, something that few satellites can say. Okay, this is where I'm going to turn it over to Danya, because he's going to talk a little bit about our latest development that we are fitting into one of these things, and it's absolutely amazing. Okay, Danya.
Thing. So we had the concept of taking one of these PocketQube size satellites, and instead of just having observations or communications, being able to observe other or inspect other satellites. So once you launch your satellite up, there's not much of a way to make sure everything's still going well and whatnot. Instead, we can have a camera mounted system on an arm. Think of like your factory robot arm, and instead have those degrees of freedom where we can look around at other satellites. This normally wouldn't be possible if you have that normal swivel base as you see on the left. It just takes up too much space. However, I had a concept of a upright planetary gear system, so we can turn more with smaller motors and fit this all into a smaller space. Our entire code base is open source. It's written in the Rust language, so we have high performance, and we don't worry about the interpretation of Python or higher abstraction languages. Are you looking for something? Oh, okay.
Yeah.
So the idea would be if we can have eventually more degrees of freedom instead of just 3 or 4, you can now find ways to turn around and observe your other satellites. Now, just to show for comparison, the reason we have that planetary gear system is because the motor is that large, and we can turn the entire arm and a camera mounted on it just through this small system in a cube, in a PocketQube. Go.
Okay, is that it?
Yep.
That's all you wanted to cover?
Yep.
Okay. All right. So we're pretty happy with the way this particular project is going, because it's new and innovative, even beyond what we were doing with just creating satellites that were this tiny. It's like now we're developing on-orbit observation of existing satellites. That includes the development of the thrusters as well as this inspection arm. We can only show information about the arm because it's fairly new. The thrusters, as soon as they're completed, we will actually be sharing with the public. But right now, can't show you that. Okay. So when we're doing this, what are the markets that we're actually looking at? Okay. And it's part of the reason why I got into making these things in the first place, other than it's rocket science and it's fun and pretty cool. Okay. We have 4 areas: Earth observation, research, military, and telecommunications. Okay. The Earth observation is where I got started. I'm a firm believer in, if you want to take care of the Earth, you need to be able to measure what's going on. Okay. It's like, if the patient, how do you know the patient is sick or well? How do you know what the problems are? Well, the first thing you do is you start checking symptoms. In order to do that, do they have a fever? And there's a simple one for if you're sick. Do you have a fever? All right. Well, you got to measure the temperature. Same thing with water monitoring. We want to use a constellation of these satellites to be able to monitor water on a consistent basis, which is not something that's done right now. Forestry management, which is another one of our issues, our market segments, gets more satellite time dedicated to it than simple water monitoring. And it's a gross thing to think about, but realize that if you're here anywhere in the Susquehanna Valley, along the East Coast, our water is pulled from generally the Susquehanna River. Berks County, I believe yours is pulled from groundwater as well as supplemented by pipes from the Susquehanna. When that water is pulled in and you have the wastewater that's treated, where does that go? It doesn't go into the ground. They put it back in the river after it's been treated. In some cases, along the East Coast especially, the outlet from a wastewater treatment plant is less than 300 yards from the intake from the next town's water supply. So if there's a problem here, it will affect there, and these two don't talk. Okay, so the idea behind the satellites was, can we make it so that we can observe these things independently and then provide that as a service to municipalities. So that's where the whole idea got started. But then we started to see other things we could do with PocketQubes. Research is one of them. Debris removal, microelectronics propulsion, or for some researchers that we're talking to, they actually want to do simple biological experiments, genetic testing on orbit to see actual changes, and then decay the satellite and destroy everything. You incinerate most of your research when you're working in a medical facility. If you hit the atmosphere at 17,000 miles per hour, I guarantee you it will be incinerated. So that's the idea, is you can do even that type of basic research. There are some things we won't carry, and if you have a question about that, I'll be glad to answer it. Okay. The military side is when we look at on-orbit satellite inspection, because that's going to be a major problem in the future. The more satellites you have up, the more dangerous this environment's going to be. If you just spent $1 billion on a satellite, would you want to spend another $1 billion to make one, or would you rather spend $250,000 and send another satellite to inspect? It might be something that's repairable. So that's where we see a lot of potential, as well as telecommunications. Internet of Things is really happening. Again, there are devices all over the globe that we could provide communications to on limited bandwidth channels. That would be a good use case for having a constellation of small satellites instead of trying to talk to 5 or 6 larger ones. The average constellation for a PocketQube can be as small as 10 or as high as 60. And that gives you incredible coverage of the planet if you have 60 satellites all passing over your area in a specific interval. Okay. Excuse me. Also, we're looking at blockchain, which is an up and coming thing for satellite communications. If you Google that or use your favorite search engine, you will find that there's a lot of interest in securing the communications between satellites. And that's one of the things that we're working on. As a matter of fact, the satellite for our client that's launching in June is specifically for Internet of Things. Okay. Now, this is our contact information. I'll come back to this slide in a little bit. But what I wanted to do is take a break from our presentation here, which we're pretty much done with it, and show you the facility that we are doing all of this work in. Okay, just like our satellites are tiny, our facility is tiny.
But efficient.
But efficient. Okay, this is, if you've ever watched the show Doctor Who, we are like the TARDIS. It is bigger on the inside than it is on the outside. The footprint of this building is 11 foot by 14 foot. That's everything we have to work with. Okay, so everything is stored in here. Every bit of the satellites are constructed in here. We do have some sub-assemblies that are, like I said, are professionally manufactured, but they end up here. So all assembly gets done in this facility. So I'm going to spin the camera. Hopefully we don't get anybody motion sick, and we're going to show you what this looks like. Whoops. Okay, I lost my zoom. There we are. Okay, so here we go. Here's the once around. Okay, so we're going to slew the camera over here to the front door. So that's the front door. From there, we have our basic, this is what we call rough storage over here. If it's something that we're not going to be using or is something of very little immediate need, it's stored over here. Up above, I don't know if it's showing in the picture, we actually have rocket parts from when I'm building rockets. There's a couple of them up there and some weights, which are an interesting, there's an interesting reason for having those. Okay, then we swing over here. You can see our electronics section. I'm going to tilt down a little bit. Okay, so this is our electronics bench. We have our oscilloscope, frequency generators, computer for checking everything. And let's go a little bit further down. There we go. And literally all of our little tiny electrical parts, electronics pieces go here. Okay, now I'm going to swing further around here. where Danya's at.
Let me skip out of there.
Okay. This is our reflow oven right here. And on top of that is our 3018 CNC machine. So if we need to make a custom circuit board and actually shape it to a specific size, we don't like doing that. We prefer commercial off the shelf. But if we need to make any changes to a circuit board, we can do that here. Okay. Next to that is our SLA printer setup. So these printers use resin in order to manufacture pieces. They're highly accurate. We can get down to, what is it, 10 microns?
I think so.
Yeah, it's like 10 microns in size. And we can push that even smaller with anti-aliasing if we need to. I always point this out. You cannot have a science lab without minions. So here's our minion. He sits on top of the refrigerator where we store all of our solder and paste that we use for making our circuit boards. This machine here is a Volterra. It actually draws circuit boards for us. So if we come up with a design and we want to test it, instead of sending it out somewhere, we actually load up a blank. It will print us the circuit board, and then we're able to test it right here, all with silver solder. It's very neat. Okay. Now, someone asked me earlier, what's up here? Everything. We have our adhesives. We keep everything is organized. Keep your facility organized. This is a disaster right now, but try and keep it organized. Know where things are. We have over on the far left there, we have all of our filament. We have our personal protection gear, tape, have a big box of tape. We have all of our standoffs, tools that we use for these various machines are stored here, science demos. We keep some Arduinos and such like that. And then over here on this side, these blue boxes are projects that are currently in development. So whatever we're working on is over here. Okay. We move in, we have our 3D printers. This is our Ender 3, it's a filament printer. Okay. And then we have our CR10, which is a large format printer. It doesn't get used much. Notice that there's lots of stuff here. We're actually working on a new electronics set using this guy. This is a Raspberry Pi Compute Module 4. This is a little board. This is what we're looking at possibly using as our main processor for future satellites. So that's what we're developing with now. That's Paul, by the way, the guy with the NASA hat. Just pay him no mind. And then further around, we have, this is a board where we do all of our design work.
And our math.
And our math. Math is good. Always do math. Have somebody check your math. Okay. A little further around, this is our another storage area that we have. This is for stuff like resins, things that we need to get to fairly quickly are stored over here, as well as miscellaneous electronic parts. And the big black box that you see there is a miniature single person class 10,000 clean room.
And then you're back to the door.
Then you're back to the door. So, and in addition to all of this stuff, down here, we keep all of our, let's see if I can do this. Okay, so that big white machine that you see there is a vacuum chamber. So we can actually test to see whether or not the satellites will survive in a space-like environment. We can freeze it and we can heat it. We can actually split it where it's frozen on one side and melting on the other side and make certain the satellite works okay. All right, and then more general storage. We have some interesting tools, and we have a drone running around here somewhere. So that's pretty much it. That's what our studio looks like. And what we do with it here. Do we have any questions? Comments, disparaging remarks? We'll take anything.
Awesome. You are literally from basement to orbit. That is crazy.
Yes, we're actually finally in discussions to get a larger facility. We're going to more than triple our space by moving into a 480 square foot facility.
Wow.
Wow, all that space.
Yeah, we won't know what to do with it. Actually,
Buy more
pretty much have
plastic
it now.
boxes.
I was wondering if a big satellite costs $1 million and your little mini ones cost only $250,000, why are people still setting stuff up with the big satellites?
There are actually two reasons why people are using big satellites. Like in the case of what's called synthetic aperture radar, which is a big thing right now for doing research. You have to have those think of it as a transmitter and a receiver, okay? In most radio systems, you can have them overlapped and use the same antenna for it, but in synthetic aperture radar, you can't. Okay, you need those two as far apart as possible in order for it to work. And generally, that's about the size of a small SUV. So for synthetic aperture radar, you do need a big satellite.
Yeah.
If you're doing television signals, like most of the television signals we get on Earth are still passed through a satellite at some point or another. Those particular systems do have to have large satellites. And this is still relatively new. We've been launching satellites since the 50s. They started off small and they worked their way up to things the size of a city bus. Then technology took a turn that they weren't expecting, and we had this massive miniaturization of hardware. The space industry is usually about 15 years behind everybody else when it comes to doing these sorts of things. So it's starting to happen. I mean, the first CubeSat was launched in 2004, and people were laughing at it. Now that 3U CubeSat is the standard size that Planet uses for its satellites. So we are getting there, and more satellite manufacturers are coming online with the idea of making smaller satellites, but it has taken a lot of time.
Now, the positive is that even over that time, we have more and more power coming by the year.
Right. And if you had when I was playing around with this in 2013, the best I could possibly do was a little tiny Arduino. And in order to get the Arduino to fit in the PocketQube, I had to turn it on a diagonal. That's not exactly conducive for launching things into space. And now I've got to fit my batteries and everything else around it. You've got limited amount of memory. Yeah, it was just what you were getting was a toy, not a tool. And so now we're actually have reached the point where we can make tools this scale that will work. Does that answer your question?
Yes.
Awesome.
I have a question. How does that, I'm a beginner, okay? Your device will go, your satellite will go on a space shuttle or a space rocket, and then it's launched into space. Is that it?
Yes.
Okay, then how does that little device survive out there with whatever debris and things are out there and meteorites and any kind of other stuff floating around?
Yeah,
How
this is where
getting ruined like.
Yeah, well, the nice thing is when I'm going to borrow from Douglas Adams to answer this question. If anyone's familiar with him, he wrote Hitchhiker's Guide to the Galaxy. All right. He said, space is big. Space is really big. Space is so big, you have no concept how really big space is. Okay. In the terms of just the orbits of the Earth, if we were to take the volume of low Earth orbit, just that volume, I can make 3 Earths out of it.
Oh my God.
Okay. It's a huge amount of space. Okay, so when Starlink is talking about putting 4,000 satellites on
with
orbit,
32,000 within the next 8 years.
Yeah, and they want to go to 32,000. You think, oh, it's going to be dangerous. No, that would the amount of space there is, even with that many satellites, it would be like being a lone car going from Los Angeles to the Mojave. I think is that Route 5?
I think so.
I don't know if you've ever been to Los Angeles. That's an 8-lane highway.
Yeah,
I've
been there. I drove from Phoenix over to Disney World in Los Angeles, Pasadena.
Okay. Yep. So you know exactly what I'm talking about, how wide that is. And you never are the only car there, right?
Well,
Imagine
I
that with
was.
32.
It felt like I was
You
about
were.
right. Across the
Oh.
desert, there wasn't anybody else but cacti.
Okay, so that's a very good example. In the middle of the desert, space is still a desert. There is not a lot there, despite what we keep talking about with possible collisions, which can happen because instead of being on the highway and everybody going the same direction, this way and this way,
You have any direction.
yeah, you have any direction. So you have people going east and west. You have people going this way and people going that way, and if they all are crossing, then it becomes a problem, especially at the speeds we're talking about. Because when we say 17,000 miles per hour, that's just a close approximation. So we're talking Mach 25 to put that into different terms. Okay. If years ago, I forgot what mission it was now, on the space shuttle, they had a paint chip from a booster get in the way of the space shuttle, and it buried itself an inch deep into the glass.
Okay, so how, that's sort of part of another question I have is how does that not get going that fast, ruined, like you said, or hit something or something, just going that speed, destroy your device? And
Yeah,
and you said I don't know what that material is. You said, I don't know, bicarbonate, what it's made of.
Yeah.
And it sounds like it's carbon, and how can it survive out in space? The material.
Yeah, the material is a carbon fiber nylon resin composite is the easiest way to put it. When we think of space as a harsh environment, space is neither hot nor cold. Okay, you're either getting radiation from the sun, or you're just exposed to the vacuum of space. Okay, so it's a radiation problem. To try and keep it as simple as possible, the cold doesn't kill you, the heat doesn't kill you. It's the difference between the two that kills you. A human being can actually survive for about a minute in a vacuum before there's before you're just not coming back. But that's the type of environment it is. It's not cold per se. There's no heat on anything that is on the hidden side.
I had the impression that they have to have like gold material on the outside of satellite so the sun doesn't, destroy it. And
well, that's for what we call thermal management. Do you know that the biggest component that's on the spacesuit that an astronaut wears is not the oxygen generator system? It's the air conditioner. You actually have to be water cooled while you're in a spacesuit because they're so well insulated, you'll overheat and die. Okay? It's the opposite problem because you're trying to protect from all this stuff. You end up like, okay,
there is no balance.
There's no balance. Yeah. So you end up like the Michelin Man in a suit with nowhere for the heat to go. So it's that radiation is the problem. And when I say radiation, I'm not talking just, X-rays and gamma rays and that kind of thing. Radiation is everything from that level all the way down to heat.
Anything that doesn't have direct contact or connection.
Yeah, anything that does, like you said, anything that doesn't have direct contact with something else can either overheat or freeze to death. So you need to keep those contacts in place. So the way we've designed our satellites is we let the CPU, which is the hottest part of our vehicle, keep the rest of the vehicle warm. So when you see that gold foil, what they're trying to do is to keep a little bit of heat in and radiate everything else out. And they found that was what worked in their situation. In our situation, like, okay, here's the CPU. Now the rest of this board won't be there when we're flying, but it'll just be this. And these get very hot. Okay, well, we can't get rid of the heat. There's no atmosphere. There's no air for it to dissipate into. Putting a heat sink on here does nothing because there's no air flowing around it to make it work. If I put a fan on it, it's still not going to help because there's no air to flow. So what you do is you build a metal connection piece here. It's made out of aluminum. And that radiates the heat away. Okay, well, now the aluminum's getting hot. So where does you need the heat to go? Well, we send the heat into our batteries to keep the batteries from freezing. Batteries need heat to function. They get too cold, they stop working. CPU gets too hot, it stops working. Oh, this sounds like a marriage made in space. Slap the two together, and away you go.
The whole system is a tight balance, right? You can't have one of this, you can't have too much of that. And it's kind of how can we use the tools at our disposal in order to create that balance?
Yep. Yeah. Thermal runaway is a potential problem. That's why we have the board. Okay, we actually work out the math to know, all right, this CPU is generating X amount of calories of heat. How do we dissipate all of that and that energy? Where does it go? Where does it need to be? Do we take too much? Do we take too little? All of that is worked out. And when we say it's rocket science, it really is rocket science.
Well, and even more than that, you have your thermo and you have your
you have
all the rest.
Yeah, you have the rocket science. So you have to know physics. You have to know chemistry. You have to know thermodynamics. You have to understand calculus.
Yeah. I quick ask this question. Somebody else is probably waiting. When you talked about the device that you could use to repair and you put the little engine in it, did you say you control that from a computer on Earth?
Yes.
Yes.
Oh my God.
As a matter of fact, we're currently in the process of constructing our own ground station here. So at this facility, even if we leave here, there's going to be our ground station antenna attached to this building. So every time the satellite passes overhead, we will actually be able to communicate with it.
Wow, that's fascinating.
So
I'll keep quiet. Somebody else might have questions. If they don't have questions, I got a couple more, but I'll wait. Somebody else questions.
Excellent question, Mary Louise.
Well, let's see. You were talking about it would monitor water. Did somebody say they have a question?
You can go ahead.
You said it can monitor water for the Earth and observe water monitoring, satellites to observe water monitoring. And I just was kind of interested in that because they say, and do you think this is true, that the water that is on the Earth now is the same water that's been here at the beginning of the creation of the Earth, like 4.6 billion years ago, whatever it is, that it goes up and it comes back down. And so the water we're drinking and using today is the same thing that's been on the Earth since it was created. So,
yes.
So that's still kind of true.
That is true. As a matter of fact, one of the problems that we have is that we're losing water.
So how are we losing water? I'm thinking there are spacecrafts coming from other planets and inner whatever solar system going under the ocean, getting the hydrogen out of our water, and then they're blaming it on climate, whatever it is, and they're getting their energy from our oceans.
Well, just a couple of things I do want to point out about, and I don't know your feelings on UFOs, but Earth is a really lousy place to be picking up the basic components you need. You want
maybe water. They're lousy ETs and they don't know any better.
That's true. I mean, if you want water, I mean, Europa's the place to go. Low atmosphere, low gravity, tons of water.
Is that one of the moons?
That's the moon of Jupiter. If you want methane or hydrogen, and hydrogen just...
Well, maybe they had a battle and they got kicked off of those moons and then they come here. We're like the poor souls.
I cannot speculate on that. What I can tell you...
What you were going to say that we have less water. So yeah. How do we have less water?
Because water is actually absorbed into the earth itself. Just like when you water your garden, it goes into the ground. Well, most surface water does in fact get stopped by the crust of the earth, and that ends up back into the system. It might take it 10,000 years, but it's still there. but we
Oh.
still lose water into the deeper parts of the mantle. That water is not recoverable. We don't have any tools to go after it. So it just ends up in the center, towards the center of the
So
earth, and it reaches.
whoever lives in the inner earth is hogging our water.
That's possible too.
They say
So-
there are different levels, and it's not it could be a hollow earth.
It could
Vern
be.
might have something to
I
say
don't-
about that.
Yeah, I don't think
I don't
so.
think
but-
magnetism agrees with that.
Yeah,
but
but the reality is that we do have significantly less water than we started with.
Yeah.
But I mean, think about this. All right, the water that you're drinking is the same water. There are molecules of that water that you are drinking that some poor dinosaur was drinking.
Oh God.
Okay.
just like the water cycle in your early
It's
bio
like the-
classes, it's still happening.
Yep. I mean, the earth water, the surface water on Earth is recycled about 7 times every year. Surface water.
Recycled, you mean it
Okay.
goes up and
So
then
that
rains,
means
or
that more than
no?
likely, if it is evaporated, it rains back down, ends up in the rivers. We process it, it ends up at your tap. Okay. And I've been in the places. I spent nearly 3 years in water quality analysis. I covered 8 states. I've seen wastewater treatment plants. I've been in a room the size of a football field under Washington, D.C.
Okay, that comes to the news lately. Where in Florida, they hacked in, they think it was from Iran. They're blaming Iran for hacking into the system in New York a while ago. I don't know if it was
Yep.
this year, something about a water plant north of New York City or Manhattan or something, and then down in Florida recently. So, okay, what can you do so they can't hack our system? Is this going to
Okay.
help that?
Yes, because when we talk about Internet of Things, like a satellite that's this big, okay, what if the security keys that they use at those plants weren't easily obtainable? If you're using a security key that's passed through the internet, there's the possibility of it being intercepted by what's called a man-in-the-middle attack.
Someone can sniff, they're called sniffing packets. Someone can kind of, if you're sending your parcel in the mail, someone can catch it in the middle or at least read it.
Right.
What if you can't get there?
Right. So the idea with an Internet of Things satellite is those keys are transmitted to the computers at these facilities without using the internet. They're over a secure channel on these. So unless you have the entire key generation set, which exists only in the satellite, you're out of
only a
luck.
client,
Yeah.
not able to
But they must have not had that. Now, where I live in Exeter, near Reading, that I got to plug in. I'm going to lose my battery. They have we have well water, but then we can use the American water system if there's some problem, and then they get city water or whatever the local water company is. So I don't think if they have well water, they have satellite stuff, do they?
No, underground water sources are not covered by satellites very well, at least not at this stage. That's one of the reasons why synthetic aperture radar could be interesting. Okay, when I talked about you needed a big satellite to do this, one of our far future projects that we're working on is, instead of having one big satellite do it, why not have 2? So one little satellite over here transmits the radar beam down, the other satellite catches the reflection.
If the key concept is that these parts have to be further apart, instead of putting artificial things in the center to make your city bus link, why not have separate units?
Yeah, so that's the idea behind it. And we are exploring that, because then with synthetic aperture radar, we can penetrate into the ground up to 20 meters. So we could measure well water in a lot of places. And so now we can help monitor and maintain at least water levels, if not water quality. And
Well,
keeping
I
track of
lived
water.
I lived in Phoenix, and they have the Arizona Canal. The water comes from the Colorado River, across the north and down the west side of northwestern Arizona, and comes across into Phoenix. And that water has the potential of being, I don't know, contaminated deliberately or from, whatever's going on above the water stream from Colorado down could
Yeah.
be radiation or defense things. And I mean, that would be, how could you monitor something like that if it's like now?
We're actually looking at using I can never say the word spectrograph. We're going to run spectrographs.
Spectroscopy.
Yeah, that's it. Thank you. The same thing we can use, instead of pointing out into space, we can point it at Earth. And when tuned appropriately, we can look for chemical traces in water. Now that has to be a significant amount of a spill. But it would be mainly used to track spills of contaminants. If you're going to deliberately poison someone by say placing 1,000 gallons of cyanide in water, no, first it's going to dilute so much it's not going to hurt anybody. But if somebody were to try something like that, it would show up on the spectrograph when we run it. So we are actually working on satellites that will do that.
You know,
So our first
Question. I have a question.
Go ahead.
ahead.
Plug
Thanks.
in.
Say more about what you have discovered about climate change from space. What kinds of things are you?
One of the biggest things. What I've done a lot of research into climate change, and first, anyone who says that the climate is not changing, they're not being honest.
Yeah.
Okay. Now, then we get into the discussion of what is anthropomorphic climate change.
Yeah.
How much are we impacting it? Well, the reality is you cannot be in a system without changing that system. Those are basic scientific fundamentals. Okay. Even in quantum mechanics, if you're there observing, you've changed the experiment. Okay. We're involved. We're in here. The amount of damage that's being done is not well known. We know it's damaged. We know that we have to do something. So the first thing we grab for is, well, CO2 is the problem. We need to get our carbon emissions down. Okay, well, that's just generally a good idea. But why is carbon dioxide causing the problems? Those are the things that need to be researched. And the idea behind doing Earth observation the way we want to with water as an initial tracking point is that we can see where water is being displaced on the planet. That gives us a piece of the puzzle. Again, we can't tell how bad the Earth is being crippled without having good information. And imagine if your doctor is going to make a decision on whether or not you need open heart surgery, and he's looking at your EKG, and he's got every three, like there are 3 heartbeats here, then there's a big gap of nothing, and then there's 2 heartbeats here, and then we got 17 over here. There's no complete set of information. We want to use our satellites to fill in those gaps so we can be making the right decisions.
Another thing I'll touch on is that I have a particular love for data science or statistics, and an important thing is that first off, we can't extrapolate. We can't say that, oh, the Earth will end in 20 years because we simply just can't look beyond our scope. Another important thing is we don't have a large enough scope, and we don't have enough of this information, whether it's a human or a computer processing it, if we don't have anything constantly observing. So in cooperation with a unit like this, or whichever other methods of collecting data, once you have a data set that's complete and you can start to work with this information, you can start to see not just what can we do to reduce certain aspects, or maybe we're completely wrong. Maybe CO2 isn't the issue and it's something else. We just don't know enough.
Yeah, and right now the scientists suspect that CO2 is the primary cause. But I've also heard that upper atmospheric water vapor, which is 10 times more deadly than carbon dioxide as far as atmospheric refraction, airplanes dump a lot of water vapor into an area that water vapor doesn't normally exist. Okay? So there are all these different intriguing pieces to the puzzle, but we don't have a complete enough picture. The idea is with our satellites, we want to help fill in those puzzle pieces that are missing, and the researchers will be given with better data. They can design better tools. With better tools, they can come up with better results. With better results, we can act in more
consequential ways.
Yeah, more consequential ways. That's a good way of putting it. So that what we're doing works. I mean, I am a fan of electrifying everything. Okay, I want solar panels everywhere. Okay, yes. My fantasy is that eventually this company will make enough money that I can buy a Cybertruck. Okay, because I need a truck. I want an electric one. Okay.
23.
But you also have to look at the cost of building that car. What is the carbon footprint of building a Cybertruck at this point? When you look at the data on automobiles, and this is a shocker, the most environmentally friendly vehicle from cradle to grave was the original military Hummer.
Wow.
Yes, it only got 8 miles to a gallon of gas, but the environmental cost of manufacturing all of those pieces from the time that it was created to the time that the vehicle is retired, it is the least environmental footprint of a vehicle. Compared to a Toyota Prius, the Hummer is superior.
So
It's
you're
often
looking at
important to
filling
look
in.
at it. I know often we focus from one angle and we don't really think about how other ways might affect, or how even the information towards, maybe like I had said, or with the Hummer example of maybe we had thought that we're moving forward, but in reality we already had an answer.
Yes. So the idea is we want to help provide that information to fill in those holes. Do I believe the climate is changing? Oh, you better believe I believe it. It's changing.
It's
It
always
has to.
changing.
Well,
It's always changing, yes.
You're looking
but
at
then-
data science, and I think there's a lot of people trying to talk.
we know the climate is changing because of human action. Whatever it
Yes.
may be doing some other things too. There may be long-term climate change things that Earth does every now and then, but
Right.
we know we're doing it, and we know we're doing it because of fossil fuels and methane and stuff like that.
I agree with you there.
Bless your research. I hope it does well, and I hope it does well quickly. but I want to take just a little exception to, we can't act until we have all the data. We will never have all the data, and we have to act anyway. End of rant. Sorry.
Yeah, and I agree with you. I like the idea of, okay, as a CEO of a company will tell you, you never have all the information. You
Yeah.
have to move.
Yep.
Okay, so go ahead and move. All right, are we going in the right direction? Now, this is where research comes in.
Yeah.
We need to continue the research to say, okay, is this direction the correct one? Or do we need to tweak the direction a little bit? Okay, a CEO,
Well,
when he
we're
makes,
running out of time.
Yep.
We're running out of time to wait to tweak.
yes, so go ahead and start the moves, start the big moves now. And then as the data comes in, you make the adjustments. That's what we need to be doing. I agree 100%. That's why I said, I want to electrify things. I don't want to be using fossil fuels. Fossil fuels are a dead end. They result in no further gain.
So you're looking at filling in some data gaps there, right? And
Looking at filling in the data gaps so that
you have a launch coming up this summer. Can you talk a little more about that in particular?
Yeah. Again, the launch in June that we're doing is an Internet of Things. It's specifically to test delivering these types of keys I was talking about to secure water treatment facilities, so that people don't break in or cause data corruption. That's what we've got to do. What happened in Florida is a near disaster. Okay? And the reality is, they had their SCADA system, which is what monitors all their water systems, runs all their pumps, runs all their tools. SCADA talks to what's called PLC. So their SCADA system was connected to a computer that was connected to the internet, and they did not train their staff to not use the same password in TeamViewer. Okay, but they had it connected to the internet because they needed to be able to transmit information back and forth from that computer set.
Yeah.
So that's where the satellite comes in. We deliver the key that keeps that information secure so that it doesn't get out. So it doesn't, we can air gap what's going on in the facility. So you send we send the key creates the information, it sends it to the cloud, it's all secure and stored, and then you can use a different computer to access it. There's no route to the SCADA system. There's no way to get to the SCADA system. That would have prevented that from happening. That's what
is that
doing.
launching on?
That is launching on the Falcon 9.
Falcon 9. All right. And so we'll look for a Falcon 9 launching in June. That's really, really awesome. Do you know what
Yeah,
orbit that's going to?
I do have to point out that, this is the space industry. All things are subject to change without notice.
Tentatively, you're looking at a Falcon 9. Okay.
Because we were supposed to launch in April. Now we're launching in June.
So
I
you were
expect
talking about, you were talking a little bit about an upcoming thruster. So we won't get into that too much. Hopefully we'll follow along and get to keep up with that. But you were talking about things that you carry to space. I suppose, through the right channels, anybody can launch anything. Certainly with a PocketQube, you can, fit what you can with it. But you also mentioned there are things that you won't carry. Can you talk a little bit about that?
I will not carry anything that could be a potential biological hazard. Full stop. Okay, what I mean by that is you don't launch a container of smallpox to test whether or not you can build a better vaccine in space, because it's not being on orbit that's the problem. It's on the way up to orbit, we had a little bit of an oopsie.
The whole, Sagan against launching any nuclear materials for powering anything along those lines of safety protocol. So biohazards, have there ever been thoughts about, and this is sort of coming off the top of my head, nuclear options for PocketQubes?
We researched a nuclear possibility with PocketQubes. The way it would work is there's a new type of battery that's been constructed. And again, even though it's minuscule amounts, we abandoned that because of the potential of a disaster at launch. Okay. Sure. Again, as you can see on my wall, I got a few big toys here. All right. Okay. When I say big toys, that's a 3/4 scale Patriot missile there. Okay. That's a model rocket. Rocketry comes in two flavors. When it works right, it's cool. And when it goes wrong, it's really cool. Okay. Really cool happens in rocketry all the time. Would you want to be the person who put a biological hazard on a rocket and then there was an accident and you contaminate an area in Florida?
Yeah, obviously there are ethical questions that you do need to isolate and reduce risk with.
Right.
Other targeted well, I'll open it up. Does anybody else have any other targeted questions? Because I know we can sort of chat for a bit here. Marion, did you have a targeted question? Oh, she just waved by. Did anyone have a targeted question? I think, Mary Louise, did you have another question?
She's muted.
Can you hear me now?
There
Yes.
you are.
It's basic. When you talked about, losing water on Earth or the carbon and climate change things, I don't understand why we have all this news about terraforming Mars. It's a dry planet. Okay. I believe they probably can terraform it, but why don't we terraform Earth if we're losing water?
That's a good conversation to have. I don't know if PocketQubes have too much to do with that. That might be a good question for our fourth Thursdays. But have you, Joe and Danya, have you guys thought about sending anything to Mars for like recon?
While we have some really cool things that we are working on with using PocketQubes in what's called a swarm methodology. So imagine having a satellite. Okay, the UAE, they just put their orbiter around Mars. Awesome. Okay, it's one spacecraft. Okay, now imagine if that spacecraft, when it got to Mars, could launch a dozen more spacecraft that all did different research and reported back to the main ship. Way more bang for the buck. So yes, we are working on that. We are actually, if anyone's familiar with what's called a Small Business Innovative Research Grant, we're actually working on several of those research areas that would include sending a small swarm of PocketQubes to the moon as part of the Artemis project.
You're talking about Artemis. That's awesome.
Yep. So we
Do you
need to
have
get
any
out there
other-
and explore.
Well, let me open it back up. Any other questions that might pertain to PocketQubes? Let's see. So you mentioned inspections of other satellites, and that was using PocketQubes instead of relaunching an identical mission or satellite. Like we know satellites can go into the billions, but you were talking about inspection. I'm curious, does that have anything to do with well, where does that go to? Would you be releasing PocketQubes to the space station that would orbit the station and potentially service and come back, or what is the scope of inspection there?
Well, the idea would be to have several PocketQubes at different orbits so that it would work like an inspection vehicle. I'm trying to think of a good analogy on Earth, and I'm not coming up with one.
Well, you can just think of like a circle, right? So if you have 3 of them here and your satellite's over here, the closer one will come over, so that you're not having one where it'll waste its thruster all the way around, and they can kind of balance each other.
Yeah, and it's going to take time to get there. Let's face it, a PocketQube, we cannot put a lot of thrust into a PocketQube. We have essentially a 50 millimeter by 50 millimeter by 8 millimeter space to put our entire thruster set into. Okay, so yeah, about that big.
All right.
Our entire
You're
thruster.
saying the antenna is actually akin to a tape measure.
Yes, it is a tape measure.
It is a tape measure. Okay, not akin. It is, in fact, a tape measure. Okay,
It is
very
a tape
cool.
measure. They actually work the best for low budget space vehicles. And I could go and buy or have the antenna designed specifically for the PocketQubes, and that will run me somewhere in the neighborhood of $50,000.
So do you mill off the paint that comes on those tape measures, or?
Yep, the paint is removed. It's replaced with a special coating, and that gets encased in Captain tape.
Okay.
So
That makes it go more than 17,000 miles per hour.
no, what that does is that allows us to receive the signals back from the satellite.
Oh,
Okay. Once the Falcon gets us to 17,500 miles per hour. Once we're there, to move a 700-gram object through space does not take a lot of thrust. It's a matter of time. It's not Star Wars. It's not Star Trek. It's orbital mechanics. And if you use orbital mechanics correctly, you can get from here to there with a little bit of help. And like this thruster will produce on the order of 10 micronewtons. That doesn't sound like a lot, but if I apply 10 micronewtons every minute as a continuous thrust for 30 minutes, now I've got a significant amount of acceleration. So that's the idea, is don't try and ram everything fast. Take your time and move slow but steady. Slow and steady wins the race. Then when you're
Sort of walks into another question. What is the timeline or usable life of one of your PocketQubes?
3 to 5 years.
5. Wow. Pretty cool for a little PocketQube.
Yeah.
Are all PocketQubes on orbit graveyard or decelerated?
Every PocketQube that's been launched so far has returned into Earth's atmosphere. We do not leave them.
Very cool.
There's been a total of 11 PocketQubes launched into space to this point. That's everybody worldwide. There's been 11, and none of
Not
them
just
are
yours, but 11 total.
11 total, and that's why it's very new. It's been hard to secure launches. Way easier today than it was even 2 years ago. And I can actually pick up the phone and call and make a phone call. And if I want to write a big check, I can be on a spaceship. I can be on a launch vehicle.
Which other rockets have you been on so far?
only, well, SpaceX, I've been on SpaceX, Antares, Firefly coming up, and Rocket Lab.
Is
SpaceX
there any-
Antares, did you say you were already on Rocket Lab?
Yep.
And you're
Your
looking at,
propulsion system is what? A fuel driven?
We're looking,
About any intent to go with ion injection?
we're looking at what's called a Hall thruster right now.
Yeah,
So basically it's an ion engine, but it still has a fuel to it.
yeah, but it's much more efficient than
Exactly. The
Okay.
ISP is somewhere around 3,200,
Yeah.
which isn't too bad. But again, it's very small amount.
that's awesome. That's more about the thrusters that, we're going to ask about in a little bit.
Yep. Hopefully we'll have a demonstration. We'll actually bring one in a vacuum chamber and you can watch it fire. I would love to
Super
do that.
cool.
And that would be cool.
I have to get Mike down from, he's in Syracuse, New York. He's the one designing our thrusters. So,
And
yeah.
I'm sure once the Mars facility, the Mid-Atlantic Regional Spaceport, gets used more and more, along with Rocket Lab's new facility there, and since you do have a history with Rocket Lab, are you looking at launching from Virginia?
Yes, we are. Most of our pocket cubes so far we've been putting into sun synchronous orbits, because that gives us, again, it's always about the bang for the buck, and a sun synchronous orbit gives us some advantages. We always fly over the same place at the same time every day. So if I want to look at what's going on here and my satellite is always over here at 2 o'clock, I can see changes pretty quick because sunlight is not a major factor. So yeah, that's where we've been going. But we do see putting a constellation up in a standard orbit, probably a 35 to 45 degree inclination. And that will help fill in what we can't see with the sun synchronous. So yeah, we'll be on Rocket Lab. The folks down at Wallops, they know who I am.
Awesome.
In order to make this work, you have to be a little irritating sometimes. You have to have
Persistent. We
some
can call it
interesting-
persistent.
Yeah.
The squeaky
Yeah.
wheel gets the grease.
Don't be afraid to pick up the phone and call them for the 8th time or the 9th. As long as they're answering the phone, it's all good. When they're not answering, that's when there's a problem. But yeah, it's been an amazing journey. I mean, Danya came on board here.
Was it 2013?
2013? Yeah.
And Danya, how long have you been with Joe?
Since October.
Since October. Wow.
Yep. So he's our youngest, brightest, fastest growing member of the team. What he's done in those few months has just been amazing. So I'm gonna tout his accomplishments. We have code that will be open sourced for driving a robotic arm in space, and the code works. The hardware is working. We'll do a live demonstration. Well, actually, we have to increase the size of the motors to do a live demonstration because the arm is not designed to work on Earth. It can't work in a gravity well. It has to be in a microgravity environment to function. So
If you used a green screen, I would probably believe it.
Yeah. I think about it. The arm, the Canada arm on the space shuttle, it can't operate on Earth. It can't lift its own weight here, but it can move its own mass. And that's the difference. So the one on Earth is actually 4 inches in diameter, bigger than the one that's on the space shuttle, in order for it to be able to hold itself together when it lifts.
And that's why math and physics is important.
Yeah, math is important. And then don't shift the decimal place, whatever you do.
So if you were to, appeal to people getting into the small satellite game, or even, different use cases for potential clients, what would you, have to say to them?
For anybody who wants to get into pocket cubes, let's say you want to build. Right now, I could use the competition. That sounds crazy, but competition means a robust ecosystem. Robust ecosystems survive. Okay. So the more people doing this, the happier I would be. For those who want to actually launch a pocket cube, what is your end goal? And what are you trying to accomplish? And then see if it can be accomplished within that space. We see water quality. I mean, the optics have come a long way in just the last few years. And the first camera, when I designed this one, the camera was a 2 megapixel camera. That was it. That's all we were going to get in this. Okay? And the limitation was really the lensing. Now with more modern lensing, we have this one, which has this beautiful, almost a third of this is lens. But we also have a 24 megapixel sensor attached to it. So larger lens, more light, better focus, more pixels means the number of pixels per meter that we get goes down, which is what you want. This sees 250 meters per pixel. This sees 20 meters per pixel. Okay. The next evolution will see a meter per pixel.
Wow.
Yeah.
That is super cool. And as technology improves, I'm sure you'll be cramming more pixels in, higher resolution, that sort of thing. So I wanted to open it up to anyone else who has another question, or if they have any other, thoughts about what we've seen, what you're doing, all of that. Any other questions? All righty. All right. And could you also, I know you stopped sharing your screen, but I think I have the contact information that I can share.
Okay. Give me just a second here. I'm gonna duck out here. Computer, do not fight me. I will win. Okay, I know there's a chat feature here. Okay, this
one of the consequences is you can chuck it into space.
Yeah, and it knows it. Okay, so I've put all my contact info in here, and I did put the street address because we do give tours. When we do have guests who are coming here, we do follow COVID protocol, so we require masks and we do sterilize. Working in a class 10,000 clean room, we have a little bit of understanding of how to keep things from being contaminated. So we follow protocols carefully. Danya and I work together. He's part of my bubble, which is why we're not masked up currently. Okay.
But even when we leave, it's still sanitized, make sure everything's clean, stay safe.
Yeah. It gets overused in my line of work, but it's not rocket science. Okay, it's medical science.
Yeah, different distinction, different discipline.
Mm-hmm. Oh, and you know the difference between a rocket engineer and a rocket scientist, right? Rocket scientist has blown one up. Okay.
Looks like from the pictures behind you, that makes you one of them.
I've had a rocket chase me down. I've had a rocket explode on the pad. I've had a rocket decide that it was not aerodynamically balanced enough and shredded itself after liftoff. And I've had what we call the proverbial lawn dart. That's where the rocket goes up. We have a non-event at apogee and it comes back as fast as it left.
I'll be sure to talk to, the experienced one over here before I attempt any of this on my own. I know that there are like model rocketry clubs and things, but I haven't been in touch with any. Hopefully, I don't know whether it's, between model rockets or launching some of this stuff, getting to know a little more about the systems that you use, how you can integrate different ones. And of course, taking a tour and seeing this from, from basement to orbit, which is the sort of packed phrase, and unpacking it is really just, blowing my mind. So it's really awesome. And I want to thank you for agreeing to chat with us about this.
I want to thank you all for attending. I mean,
Thank you.
It's very interesting. Thank you very much.
Thank you.
and again, if you want to take a tour of the facility, have any questions, my email is there. Give me a quick call. We'll arrange a tour. We usually do tours of no more than 2 people, simply because the building can't handle more than 2 people.
And after post-pandemic, of course, it's still
Yes.
pretty low numbers for tours. So we'll have to look into that. Nothing immediately, but of course, we'll definitely be in touch. Definitely keep up, and good luck. I guess Godspeed's the word if you're launching soon. So
I didn't show them the big one, did I? No, I didn't. And all of this, I just noticed. I didn't show you our latest design.
so the grand finale.
Grand finale. Okay. So this is what a PocketQube looks like with a 10-watt solar cell system on it. So it's like origami.
Will unfold.
Yeah, it'll unfold. This one doesn't, because we were experimenting. We're deciding whether or not this is going to be enough of material to hold it together. So this is actually a sag test. So sitting here, and we apply heat to it as if the sun were radiating it, and we watch what happens to the components. It needs to survive over time. So
Very cool.
we'll probably introduce springs.
Very cool. Well, I know you're looking at launching more. You're looking at not just building bigger, building not smaller, packing more into smaller spaces.
Yes.
Either way. And if you need anything with radio, I might be able to help you out with something, whether it's ground stations or some, ham know-how.
We'll talk.
We'll definitely be in contact about that.
All right, cool. Again, thank you, everyone. I know this probably ran a little longer than you were expecting, but
Thank you.
This
for
was
sharing.
awesome, and I'm loving every second of it. So I want to thank you, Danya, for joining this. Sorry I butchered your name at the beginning, but I'm excited to see what you do with Joe here. Joe, thank you for bringing us, into the workshop, the brains of the organization, and by organization, it's not what's on the bench.
yes.
So it's super cool to have a lens into this, if you will. So I'm going to stop with the puns and cut you guys loose. Thanks so much.
All right.
And we appreciate what you're doing, and we'll be sure to follow up with you.
All right, sounds good. Take care, everybody.
Good luck in June.
All right.
Bye.
Have a good one.
Safe.
Right there.